Ladies and gentlemen, my name is Daniel Almeida. I work for Collabora, and today we're going to be talking a little bit about porting the Nouveau Image Library to Rust. The Nouveau Image Library is a part of NVK. It's the part that's converting from VK image to actual device addresses and device-specific commands. And another title that I have for this presentation is Rewrite It in Rust. A rewrite it in Rust strategy that actually works, and we'll see why this is the case in a couple of minutes, basically. For the agenda, we're first going to start with some initial considerations of when is it easy versus when it's not easy for you to basically introduce Rust to your project. Then we'll go over how you go about choosing a component to port to Rust, what makes it a component a good candidate to be ported to Rust. After that, we'll be talking about the actual porting process. How does this look like? The memory management side of things. We'll see that there's some corner cases in there that we have to pay attention to. And lastly, how do we debug this? So to start with, when is it easy to introduce Rust in your project, right? Assuming that you're starting off from some pre-existing project that has a whole lot of C code already. So basically, if you want to just add a Rust binary, that will be relatively easy. If you somehow already have support to compile Rust files, and you already have Rust files in there, and now you just want to write a library that will link against your pre-existing Rust files, that's also somewhat easy. So in other words, when we have a feature that's been relatively isolated from the rest of the project, that's good. On the other hand, if you have a feature that has not been isolated from the rest of the project, or when you basically want to have code in Rust that you can call from your pre-existing C code, and you have a huge project in C, that's when it's not that easy, but it's still doable. We'll see, right? And to choose a component, hopefully you're going to start with something small, right? Something that exposes a small public API, something that's self-contained. You don't want something that has a whole lot of functions that will be called from a whole lot of different places in your C code base. This is just going to be a mess. You should choose something small with a small public API first, definitely. And once you choose this component, then you can jump into the actual porting process. I want to highlight the code I've added here on the left-hand side. I have a otherwise regular Rust function that I've named call me from C. Again, this is just a regular Rust function. The only difference is that it has this no mangle annotation on top, and it has this extern C, thing before the fn function token. And the idea is that we want this function to be, as the name implies, something that we can call from our pre-existing C code. And in order for this to happen, the first thing we have to do is we have to disable mangling. And the reason why we have to disable mangling is because Rust, like C++ and many other languages, they use mangling as a implementation strategy to basically implement like generic parameters and closures and namespaces and other stuff. It will use the name of the symbol to actually encode all of this information. This is troublesome because you want a one-to-one match between the what you call your function to the actual name that will be in the actual object file. Because from C, you basically you don't want to type. This is actually pretty unworkable. This huge name that you're seeing over there. You want the name of the function you write in Rust to be the exact name of the function you'll be calling from C. And that's why you need to disable mangling. So you lose access to all of these things, to generics, enclosures, and namespaces for your public API, not for the rest of your code, but for your public Rust API. But that doesn't really matter, because, well, once you translate that to C, C doesn't really understand any of these things anyway, so we're not losing anything. And the extern C token is basically to make sure that the machine code that's emitted by the Rust compiler can actually be called from C, right? And turns out that if you emit this machine code and you tell the linker how to find it, the linker will link against your function, and you'll get a dynamic switch between the two languages at runtime. Nice, right? So now you will have to port your underlying component to Rust. That's on you. I assume you know how to do that, because here in this talk, we're talking about how to interop things between Rust and C, right? So you will port your underlying component to Rust. And once you're done, the idea is that you will write your public API as per above, like using this no mingle and extern C stuff, right? And once you do that, these functions will be able to be called from C. And then you will basically call this function from C at a later point. And now, as I said, we need to make the linker aware. We need to make C aware that these functions exist. And the idea is that you will need a prototype. And that's not something that's specific to porting things to Rust or anything. Even for regular C code, if you want to call a C function from another translation unit, right? You need to have a prototype. If you want to call even a function as defined within the same translation unit, if it's defined below where you are, you also need a prototype. So it's no different here. And you can hand type a prototype. You can create your own header file, typing everything by hand if you want to, and it's going to work. But it's not a good idea because things can get out of sync, right? Let's say your function now takes an argument. Over here, this function is trivial because our call me from C function doesn't take any arguments and doesn't return anything. So it's actually trivial for us to just, write by hand a C version of that returns void and doesn't take any arguments. But as soon as you take arguments, let's say you take a pointer to struct foo, and now in your Rust code, you add a field or something along these lines. Now your Rust version may not match your C version of struct foo, and that's where a whole lot of nasty bugs can start to creep in, and you don't want that. Things can get out of sync relatively quickly. It's not a good idea. And the good thing is that there's a tool called cbindgen that can automate this process for us. It can automate the process of generating a header file that we can then just bout include in our C code. And as it's a tool, it's a computer tool, it will, every time you run it, it will make sure that things are in sync and, ensure API compatibility. And it works recursively. So the way it works is it will, start looking at your Rust code and see, every time you have a public function with no mingle and the extern C tokens, that will, cbindgen will basically write a equivalent C function prototype for that. It will collect all these function prototypes into a header file and give you this header file. And the good thing about it is that it works recursively. So if it sees that your function now takes a pointer to a struct foo, or in Rust terms, a reference to a struct foo, it will be like, wait a moment, what's a struct foo? I should generate a equivalent C version for struct foo as well. And the reason why cbindgen can generate an equivalent version is because for each and every type that we want to basically exchange between the two languages, we have to annotate them with repc on the Rust side. And repc basically tells the Rust compiler to lay out this type in memory exactly like a C compiler would, right? And because the default is rep Rust, which is not stable, therefore the two languages could not interop, they would not agree on how the type looks like in memory and blah, blah, blah. But if we use this repc annotation on top, then it actually matches, like the layout between Rust and C matches. And this means that we can basically share structures and share our enums between both languages completely fine. So the summary so far, you choose a small self-contained component, you port that to Rust, you ask Rust C to generate the machine code for that. We have a special, annotation for the public API so that C can call this public API. After that, after you call the public API, the code inside of your public API can call other Rust code without extern C or polynomial mingling. That's just for the interop layer between the two languages. And after that, you use the cbindgen tool to basically parse your public API and generate a equivalent header file with function prototypes. You bound include this header file in your C code, and then you can call your public API from your C code. Thereby, you can interact with the Rust version of your component from your C code. That's the big picture, right? And for memory management, we have to be a little bit careful because some types in Rust, they will allocate, and Rust has this idea, this RAII idea, it's sort of borrowed, quote unquote, from C++, where you basically acquire resources, and at some later time, once the Rust compiler notices that your type is going out of scope, it will place a call to basically free your resources, and this call is called drop, right? And if your type implements drop, I have an example with a vec. A vec is basically a resizable array in Rust, and that will allocate, right? It's equivalent maybe to std vector from C++, let's put it this way, kind of. And that will allocate, and once Rust sees that this thing is going out of scope, it will attempt to drop that. And we have to be a little bit careful on how we're going to basically do the interop between Rust and C here, because now we need to make sure that we have a way to transfer ownership of the vec. I'm just using vec here as a stand-in for any type that allocates, basically, any type that implements drop. You basically need to have a way to transfer ownership of this type to C, and then give C a way to transfer ownership back to Rust so that this type can be freed once the C code decides that it doesn't really need that object anymore. And again, here I have an example for vecs. You can disassemble the vec. You basically will, pass to C the pointer, the size, and the capacity, and you will have this memForget call. This memForget call will just tell the Rust compiler, hey, please do not include a call to drop here, because otherwise the vector would be freed and we would be dealing with uninitialized memory from the C side. We don't want that. So we use this memForget call to say, hey, we're transferring ownership of this vec to the C side. Please don't touch this from the Rust side for now. Do not free this, from the Rust side for now. And the idea is that we also provide this foolless destroy thing, which will take, again, the pointer, the size, and the capacity that we previously made available to the C side. We'll take that back from C, and then we will reassemble the vec. And then at this point, once the vec is reassembled, it will go out of scope and it will get dropped. Thereby, the memory will get freed. And that's how we will give C a way to basically free the memory once it's done with it. There's no cookie cutter solution. You have to find a way to, disassemble your type and transfer ownership to C, and then reassemble your type back in Rust so that you can free it, basically. And I told you that for all types that you want to interop between the two languages, you have to have this rep C annotation. That's actually not true, right? The truth is you can have known rep C types, but if your type is not rep C, then it becomes opaque to C, right? You cannot, the C part of your code will not be able to access any of the fields or anything. It'll only be able to access your type via a pointer, right? And this is good and bad. It's good because, from one end, you get to have more complex types, which are not rep C most of the time, like vec is not rep C. Maps are not rep C. Most containers in Rust are not rep C. Most of the types in the standard library are not rep C. So you get access to these things. But the bad thing is that now you need to heap allocate these types. You need to have them behind pointers. You need to add this pointer interaction so they have to live on the heap. And, there's a good part to it and a bad part to it. And here I have an example of a struct foo, which only has a integer within it. And we have 4 functions. We have a function that creates this foo struct. We have this foo struct will, by the way, be reference counted so that we can have multiple references at different points. It will have a mutex inside so that if you're accessing this thing from different threads, we can do so in a thread safe manner by locking this mutex. And the idea is that we will provide C with these 2 functions. So get and put. Get and put will increment and decrement the ref count. And then the do stuff will basically, this is just a stand-in for functions that would actually do some interesting work. Our do stuff will basically reassemble the reference counted pointer and then lock the mutex and then increment the integer inside. That's how it works between the C and the Rust version. And once C decrements the ref count and the ref count goes to 0, it will get dropped by the Rust side, basically. And that's how the header file looks like. It's basically, you get a prototype for the 4 functions. This mutex foo thing is opaque type that you can only, it's forward declared, you can only interact with it through pointers. And basically the new function, you get a pointer from it, and then you pass those pointers to get and put and do stuff. That's how it works. And now going back to Neil one last time, because once you understand how the process looks like in general, I think it becomes pretty clear on how I made this work with Nil. I had basically the two implementations side by side. I ported it to Rust, and I had basically the C implementation and the Rust implementation side by side. So every time let's say this, in the example here, I have Nil image init. I now also have Nil rs image new, which also creates a image, but now using our Rust component. These two things are operating side by side. And the idea is that I had these asserts everywhere. That basically every time I had a version in C and a version in Rust, like a function calling C, a function calling Rust, I would assert like some things to make sure that the two versions matched along, each path where the component was being called, where the C component was being called. I would add a call to the Rust component and assert that the two data structures were a perfect match between the two, let's say. And at first, the asserts were obviously hitting a triggering all the time, but after debugging this for a while, they did not trigger anymore. And that's when I knew that we could remove the C version and have only the Rust version. And we could also drop this RS stuff from the name of our functions and basically remove the C version completely. And this is upstream. This is already working for a couple months now, and this is the overall strategy. And the idea is that you can take this strategy and you can apply this strategy easily to other components in C projects like Mesa, so long as, again, you identify a somehow self-contained piece of the code base that you want to apply this strategy to. I think that's a strategy that can scale for the project. That's the strategy that's being used, like, let's say in Firefox and in other projects as well, to slowly port them to Rust. And that was what I had to say to you guys today. Thank you. We're hiring, and see you next time. Bye bye.
So you mentioned you can create a Rust definition in the header file and use a tool to generate the C header file. But if you're using Rust to reimplement an existing library, you ideally want to use the C header file. Is there a way to generate a Rust header file from a C header file, or include the C header file in Rust instead of doing it the other way around, to make sure you have the same types as you did before?
If you can do it the other way around. So what I did was to be really real careful thing down, and then I asked cbind to generate it and then compare manually. That's what I did. I have no idea whether you can do it the other way. Say that you probably, I think you probably can't, to be honest.
Oh, that seems very unfortunate. It seems like the language.
Yeah.
I think you might be able to by having the C, by including, at least for function prototypes, by including both in the same C source C file, and then the C compiler will, if you have different prototypes of the same function, the C compiler will complain.
Yeah, I could. Yeah, I have no idea. I didn't try this, so yeah.
There's actually a tool called BindGen which does the opposite direction. You take a C header and it's generating your Rust definitions. So that's possible and works.
Yeah, I'm aware of it. Yes.
Quick question. For the mutex foo example, is there a specific reason why it's returning result by pointer, but not by function result?
If it's returning a result by point, what do you mean?
Because you are passing a pointer to where it will write the return value, but the function itself doesn't return anything.
For the new function?
Mutex full example.
Yeah, but when you say you're passing a pointer, are you referring to the new function that is assigning a pointer, the one that takes a dual pointer?
No, it's. Can you show the slide, or it's? It wasn't the video, yeah. So you're creating a mutex object there, but you're not returning it by value from the function. You're passing the pointer where it will be written as a function argument. Why is that?
No, I don't think there's any reason. I think you can do it both ways.
Okay, so it's just an example. Thank you.
Is it possible to access non-RepRC Rust data types from C, or at least avoid the extra allocation by manually passing the right size of and offsets if necessary, so that C knows how much to allocate, even if it's not, and then just if you want to access a field using manual pointer arithmetic?
Well, the usual thing to do with non-RepC types again is to treat them as a fake. I guess you could poke in there if you are inclined, but again, as the type, as the type is non-RepC, I don't think you can actually know where exactly you're indexing with it, the data, right, within the memory. So, so your question was, can you repeat the question just to make sure I answer that?
So could you, Russ, so even non-RepC types, and I guess there's also rep-packed, which is also a defined layout, but for types with an unspecified layout, Rust, there is still a known size. You just have to ask the Rust compiler for it. So could you pass that to something and say allocate this much memory, and then the Rust side writes to that much memory? Or would that just be overly complex in the cases you've dealt with?
Yeah, I don't think this helps anything. I mean, ideally, because the obey thing is also very convenient, because for the mutex example, I'd say like Rust doesn't know anything about Rust's mutex, so it doesn't really. There's no point in poking there for whatever reason. And also, I mean, I think it's convenient to have Rust in charge of the allocation and deallocation instead of trying to push that to C somehow. So yes, I think even if we could do what you're suggesting, I think that's a little bit counterproductive. That's at least my opinion.
Hi, thank you for your talk. I'm wondering high level, so I can understand the advantage of, say, writing new code in Rust, but are you finding it advantageous, or what advantages are you finding of porting old code that already exists in C to Rust?
Can you repeat the rest of the question? What
advantages are you finding from porting existing C code to Rust?
What I like about porting, existing stuff to Rust is that we can be more expressive using the type system and stuff. We also can use the Rust standard library, which again I think is gives you a little bit more of expressiveness maybe. So I mean, ideally you want to basically start from scratch, but that's not realistic, So I guess that what I'm talking about here is that you take what you can get, right? It's not as good as starting over from scratch, but still you get some of the things that Rust will provide you again the type system and the use of the Cinder library and blah, blah, blah. I think that in particular, if you're writing Rust code, it's good that if you're taking a reference, let's say, you know that this reference is valid, so you don't have to basically worry about, taking a pointer and then this pointer being null, that type of stuff. So I think it helps you basically weed out these types of errors. That's where I think the advantage is.
Okay, thank you.
Thank you, Daniel.